Good afternoon to everybody. Actually, previously, 2 days back, we have uploaded normal distribution part 1. Actually, I want to give lot of examples and lot of explanation for normal distribution. But for normal distribution, it is a major thing we have to understand for any data scientist for data analysis. So I have given another part 2 for with examples. Then we will see the beauty of the normal curve first. No matter what mu or sigma are, the area between mu minus sigma, mu plus sigma is about 68%. The area between mu minus 2 standard deviation and mu plus 2 standard deviation is about 95%. Area between mu minus 3 standard deviation, mu plus 3 standard deviation is about 99.7%. All the values fall within the 3 standard deviations. This is the bell-shaped curve. 68, 95, 97, 99.7 rule. Here you can have a beautifully a bell-shaped curve has come. This is the mathematical terms. The integral part of mu minus to mu minus sigma plus sigma, mu minus 2 sigma, mu plus 2 sigma, and mu minus 3 sigma into mu plus 3 sigma. These are the formulas. Here 0.68 dx and dx is 0.95 and dx is 0.997. Okay. How good is rule for real data? So it is a normal distribution. We want to know how it is good for our real data. That means the data application, how it is good. The mean of the weight of the woman is 127.8. The standard deviation is 15.5. Okay. Then you can find out here 68% of 120 is 0.68 into 120 is equal to 82 runners. In fact, 79 runners fall within 1 standard deviation of the mean. These are the graphical representation. This is for 95% of 120, 114 runners. This is the graphical representation for 95%. This is 99.7% of 120, 0.997 into 120, 119.6 runners. In fact, all 120 runners fall within 3 standard deviation of the mean. Suppose this is one example. JAM scores roughly follows a normal distribution in the Indian population of college-bound students with a range restricted to 200 to 800, and the average JAM score be 500 with a standard deviation of 50. Then 68% of students will have scores between 450 to 550. 95% of will be scores between 400 to 600. And 99.7% will be between 350 to 650. But what if you wanted to know the JM score corresponding to the 90th percentage? That means for 90% of students are lower, is equal to 90% of students are lower. So P is less than or equal to Q is equal to 0.90. This is the formula. Solve for Q by looking at tables. This is the standard normal distribution. All normal distribution can be converted into the standard normal by subtracting the mean and dividing by the standard deviations. Somebody calculated all the integrals of the standard normal distribution and put them in a table. Standard normal universal currency, the formula for the, these are the formula for the standardized normal probability density function. And comparing x and z units. Here 100, 200 standard 0, 2.0, x mu 100 standard deviation 50, here mu 0 and standard deviation is 1. Example, for example, what is the probability of getting a math JAM score of 575 or less? Mu is equal to 500 and sigma is equal to 50. Z is equal to 575 minus 500 dividing by 50 is equal to 1.5. A score of 575 is 1.5 standard deviation above the mean. P of x less than or equal to 575 is equal to integral of 200 range from 575 1 by 50 of 25 into exponential of minus 1 by 2 s minus 500 by 50 into whole square dx. But look up, z is equal to 1.5 in standard normal chart of 0.9332. Practice problem. If birth weights in a population are normally distributed with a mean of 109 OEZ and standard deviation of 13 OEZ, what is the chance of obtaining a birth weight of 141 OEZ or heavier when sampling birth records at random? Z is equal to 1 minus 141 minus 109 dividing by 13 is equal to 2.46. From the chart from the chart of Z table, 2.46 corresponds to a trade tail greater than area of 2.46 equal to 1 minus probability of Z less than or equal to 2.46 is 1 minus 0.9931 is equal to 0.0069 or 0.69 percentage. What is the another problem? What is the chance of obtaining a birth weight of 120 or lighter? 120 minus 109 dividing by 13 is 0.85. From the chart of Z tables, 0.85 corresponding to a left tailed area of PZ less than or equal to 0.85 is equal to 0.8023 is equal to 80.23. Looking at probabilities in the standard normal table, here what is the area of the left of Z? 1.51 in a standard normal curve. Area is 93.45%. You can see Z 1.51, 1.5 upper 0.01, so 1.51 exactly 0.9345. Area is 93.45. Our value is 0.9345. Area is 93.45. Is my data normal? Not all continuous random variables are normally distributed. We should first think whether it is a normal or non-normal. We have to find out that there is no assumption that all continuous random variables are normally distributed. It is very important to evaluate how well the data are approximated by a normal distribution. The normal probability plot. The normal probability plot is a graphical technique for normality testing, assessing whether or not data set is approximately normally distributed. The data are plotted against a theoretical normal distribution in such a way that the points should form an approximate straight line. Departures from the straight line indicates departures from normality. The probit function of the quantile function associated with the standard normal distribution pi of minus 1.96 is equal to 0.025 1 minus pi of 1.96. Normal probability part, order the data, find corresponding standardized normal quantile values, plot the observed data values against normal quantile values. Evaluate the plot for evidence of linearity. Normal probability plot copy. This is an example, right skewed concave up. Normal probability plot love of writing. Neither right skewed or not left skewed, but a big gap at 6. Right skewed concave up. Here plot of exercise. Plot of wake up time closest to the straight line. From the above formal test for normality, the results of coffee, strong evidence of non-normality, p less than 0.01, writing love, moderate evidence of non-normality, p is equal to 0.01, and weak to no evidence of non-normality, p is greater than 0.10. Wake up time, no evidence of non-normality, p is greater than 0.25. Normal approximation to the binomial. When you have a binomial distribution where is n is large and p is the middle of the road, not too small, not too big, closer to 0.5, then the binomial starts to look like a normal distribution. In fact, this does not even take a particularly large n. Recall, what is the probability of being a smoker among a group of cases with a lung cancer of 0.6? What is the probability that a group of 8 cases you have less than 2 smokers? When you have a binomial distribution where n is a large and p is not too small, then the binomial starts to look like a normal distribution. This is the smoking example. Z is equal to minus 2, p of z less than 2 is equal to 0.022. Exact binomial probability is 0.00865. So based on that, p of z less than 2 is 0.022. A little off, but in the right ballpark, we could also see the value of the left of 1.5. Z is equal to 1.5 minus 4.8 dividing by 1.39, which is equal to minus 2.37. P of S less than or equal Z less than or equal to minus 2.37 is 0.0069. A fairly good approximation of the exact probability 0.00865. Practice problem. You are performing a cohort study. If the probability of developing disease in the exposed group is 0.25 for the study duration, then if you sample randomly 500 exposed group, what is the probability that at most 120 people develop the disease? P of x less than or equal to 120, P of x equal to 0 plus x equal to 1, so and so, so and so. Or use normal distribution, u is equal to np is equal to 500, 0.25 is equal to 125, and sigma square is equal to np into 1 minus p, 93.75, sigma is equal to 9.68. So z is equal to 0.52, probability of z less than 0 minus 0.52 is equal to 0.3015. Case study. A company supplies pins in bulk to a customer. The company uses an automatic lathe to produce the pins. Due to many causes, vibration, temperature, wear and tear and the like, the length of the pin made by the machine are normally distributed with a mean of 1.012 inches and a standard deviation of 0.018 inch. The customer will buy only those pins with the lengths in the interval of 1.00 plus or minus 0.02 inch. In other words, the customer wants the length to be 1.00 inch but will accept plus up to 0.02 inch deviation on either side. This 0.02 inch is known as the tolerance limit. Here, one question, what percentage of pins will be accepted by the customer? Answer, normal distribution 1.02, 1.01 so and so is equal to 2. True. Normal distribution 0.98, 1.012 and 0.018 true. It's equal to 0.633917177 using MS Excel. It means that around 63.4% of the nails will be accepted by the customer. In order to improve the questions percentage accepted, the production manager and the engineers discuss adjusting the population mean and standard deviation of the length of the pins. If the lathe can be adjusted to have the mean of the length to any desired value, what should be it adjusted? Why? The mean length should be big 1 because that is what customer wants with a tolerance of 0.02. In the case study example it is there. So same thing is our answer. Question: suppose mean cannot be adjusted but standard deviation can be reduced. What maximum standard deviation would make the customer accept? One is 95% of the sample and 99% of the sample. A, we know that 95% of the values lie between plus or minus 1.96, therefore 1.02 to minus 1.012 dividing by 1.96 is equal to 0.004082, which is a new standard deviation. The same thing for 99%, 0.003101 is a new standard deviation. Another question, the production manager then considers the cost involved. The cost of resetting the machine to adjust the population means involves the engineer's time and the cost of production time lost. The cost of reducing the population standard deviation involves, in addition to this cost, the cost of overhauling the machine and re-engineering the process. Assume it costs $1,50,000 a square to decrease the standard deviation by X inch. Find the cost of reducing the standard deviation to the values found in previous question. So for 95% $29.06 and for 99% $33.30. Another question, a survey showed that 95% of the users use as their browser. The problem can be randomly select 200 people. What is the probability that exactly 194 say yes? The problem can be approximately as normal having mean NP 200, 0.95 is equal to 190 and variance equal to 9.5, which are greater than 5. So exact percentage of error is 8.9%. Conclusion, normal distribution can be used to describe many real life situations and are widely used in the fields of science, business and psychology. They are the most important probability distribution in statistics and can be used to approximate other distributions such as discrete binomial distributions. The most incredible applications of the normal distribution lies in the central limit theorem. This theorem states that no matter what type of distribution a population may have, as long as the sample size is at least 30, the distribution of sample means will be normal. If the population is itself normal, then the distribution of sample means will be normal no matter how small the sample size. Thank you, my dear friends.